Hey everyone, this is Devin Sheets with Alpha Sound. In the last video, we discussed the basics of cardioid subwoofer technology, and I offered a few thoughts on what NEXO might be doing to make theirs work so well. Since then, I've explored even more about this situation, and so I'd like to go into more detail. To summarize what we already learned about cardioid subwoofers, they are basically achieved by using an additional rear-facing subwoofer that has a polarity flip and a digital delay added to the signal. Each waveform from the front subwoofer is met by an equal and opposite waveform from the rear, and there is a cancellation of the sound traveling in the rear direction. As we saw, the ability of the waveforms to sum in the forward direction is dependent on the frequency, with some frequencies summing perfectly and others not so well. To fix this, I suggested that companies like NEXO might be applying a different delay time to every frequency in the rear as a kind of compromise, getting the best possible summing in the forward direction while sacrificing as little cancellation as possible in the rear direction. However, this analysis was only taking one dimension into consideration, forwards and backwards along a straight line. We need to look now at what is happening in two dimensions, both along the x and y axis. As we'll see, things are a bit more complicated. Let's take a look from a bird's eye view above two subwoofers. We'll draw a line on the ground around them that represents that point at which you would always hear the same volume from the subs, no matter where you stood on the line. For these omnidirectional subwoofers, we would simply draw a circle, because as long as you always stand the same distance away from the subwoofers, the volume will sound the same anywhere you stand around them. With cardioid subwoofers, we can see that in the rear direction, there's a strong cancellation effect, forcing you to have to stand very close to the subwoofers to hear any volume at all. As you move around to the sides, the cancellation starts to wear off, forcing you to have to move further away in order to keep the volume the same. By the time you reach the front, there's a summing effect, and so you'd have to be quite far away in order to maintain the same volume. These lines are called polar patterns, and it's how we map the general cardioid response of any given setup. For reference, let's go back to our omnidirectional subs. All waveforms would have a summing effect in all directions, so we get a circle. If we flip the polarity of one of the subs, we get a figure 8 pattern. This is because the waveforms cancel each other at every point that is an equal distance between the two subs, represented by this line. As we begin to add delay to the rear-facing sub, we can see the polar pattern begin to change, favoring cancellation in the rear and summation in the front. However, the cancellation in the rear is not completely in the rear direction, but rather it is split into two cancellations off of each side. Eventually, with enough delay, the two will converge into one rear-facing cancellation, with the fullest amount of summation in the front. And if we keep adding delay, we start to lose cancellation altogether, and the subs return to an almost omnidirectional pattern. Going back to true cardioid pattern, it is important to notice that when we increase or decrease the frequency, the rear cancellation stays the same, but the forward summation is affected, just as we saw in the previous video. Now, when I said that a bit of cancellation had to be sacrificed or lost when we nudged the delay times in the rear on a per-frequency basis so that the forward summing could be maximized, that was only half true. For some frequencies, what is actually happening in the rear is that the cancellation point is not being lost, but rather being split into two in the XY plane. For example, here's the perfect cardioid polar pattern at 50 Hz. And down at 30 Hz, we do start to lose cancellation with the adjusted delay, but up near 80 Hz, we can see a split in the cancellation pattern. Now, filling in for a few other frequencies in the subwoofer range, we can see the overall cardioid patterns formed by doing this delay adjustment at every frequency, which I believe NEXO may be doing to their cardioid processing. Stacking these polar patterns in a vertical alignment like pancakes helps to visualize the end result. Now, let's go back and forth here a few times to really see the difference in both forward gain and cancellation pattern between these two methods. Now, there are pros and cons to each. In situations where you need the maximum volume from your subwoofers, and you want to generally avoid spilling bass information behind the subs, but don't really mind exactly where the cancellations at every frequency point, using the adjusted delay method is a good option because you get maximum forward summing and a strong average cancellation behind the subs across the frequency spectrum. For example, in a large arena with a rock band, maximum volume is of course needed, and any rear cancellation in any direction is helpful because it keeps bass frequencies from bouncing off the back and side walls, causing muddiness and comb filtering. However, in situations where you need a very specific and consistent direction or angle for the cancellation at every frequency, and can afford slightly less output from your subwoofers, which we'll talk about later why that is. Having a fixed digital delay at all frequencies can be a good option. Because suppose you have a sensitive microphone on stage that you need a lot of gain out of, like a cello or tuba microphone, and you need a lot of gain over a wide range of frequencies, and the microphone is in a very specific spot on stage and doesn't move around. Being able to land that cancellation point right on stage where the microphone is placed can result in an incredible amount of gain before feedback and an amazing sound from the subwoofers. Depending on the physical distance between the subs and the delay that is chosen, the cancellation can be pointed wherever it needs to be, no matter where the subwoofers are placed in front of the stage and no matter where on stage the mic is. At Alpha Sound here in Oregon, we use this method quite often. When we need to mic taiko drums for our local world music festival, the Salem World Beat, we configure our NEXO subs to have a cancellation angle of 45 degrees so that it lands directly on stage. And then we place a condenser mic directly in that cancellation null zone so that we can turn it up in the subwoofers and get a lot of gain down to 30 Hz from drums that may be 10 or even 20 feet away from the mic. It's quite amazing to hear it work so well. We also did this for a Joshua Bell concert at the Elsinore Theater here in Salem, since the cellos and basses were literally right up against the sides of the subwoofers. In that particular situation, the subs were configured in a kind of asymmetrical cardioid pattern, but the idea is the same, to land the precise cancellation point at all frequencies right where the mics are. We had all the low-frequency gain we wanted, and the result was a deep and powerful sound from the orchestra as a whole. In each of these situations, we use the omnidirectional processing on the NEXO amplifiers and our own separate processing to configure the cardioid pattern using polarity reversals and delays and such. But we also use NEXO's cardioid processing, for example, in this situation, where our S118 subs are flown at the Keller Auditorium in Portland, and we needed maximum volume from such a small number of subs, and we didn't have any specific microphone or location on stage which needed strong cancellation at all frequencies, so we used their back-to-back cardioid mode on the processor, and it worked very well to tighten up the sound of the bass overall while allowing for maximum forward volume at every frequency. Now, before we go even deeper into this, let's take a minute and wrap our heads around some graphs. This is a phase plot with the degrees of phase here and the frequencies here, and what is being measured is the relative phase of one subwoofer against the other. So for example, with two omnidirectional subs next to each other, the plots would look like this because all frequencies from each sub are in phase with all the others all the time in all directions. If we flip the polarity of the rear subwoofer, we can see that the plots both show a plus or minus 180 degree change accordingly. If you remember, this was our figure 8 polar pattern. As we begin to physically move the subs apart, we can see that the different frequencies begin to have different phase relationships because they have different wavelengths. Adding some digital delay to the rear signal will bring the rear direction's phase relationship back to 180 degrees at all frequencies and will have a cancellation effect. In the forward direction, we can see that 50 Hz is perfectly in phase and sums nicely, producing an ideal cardioid effect at that frequency, while the surrounding frequencies begin to move away from 0 degrees of phase, either positively or negatively, it doesn't matter. The point is that their summing will not be as strong, and there will be less forward volume at those frequencies. As we've already explored, nudging the digital delay times around in the rear can increase the forward summing, which will produce a rear phase plot that looks something like this. But the cancellation pattern becomes more angularly distributed per frequency, as we've already noted. So take your pick depending on your application. Again, I'm doing a lot of speculation and reverse engineering here, and could be wrong about some things. But here's what the NEXO processors seem to be doing when I look at their outputs with my analyzing software. Here's the early generation of NEXO Cardioid Subwoofers, the CD series. To get these measurements, I added an amount of delay to the outputs of the NX-amp processor, which correspond to the real physical distance between the front and back of each subwoofer configuration, and then compared them with a transfer function using a speaker-to-line level converter out of the amp. It seems that what we have are slightly different delay times per frequency in the rear, and a forward summing that resembles a maximized setting. The effect is that the CD series has a slightly different cardioid polar pattern in different frequency ranges, resembling something like what we modeled earlier. Perhaps this was intended to allow the CD series to have maximum forward output as a cardioid sub, which could best compete in the loudness wars. So too with the S118 cardioid modes, slightly different delay times in the rear for what appears to be a maximum forward amount of volume. Who knows? As fun as it is to guess about the inner workings of the NEXO R&D department, the thing we can be sure about is that the NEXO cardioid subs from the CD series all the way up to the S118 and beyond perform better than just about anything else on the market. At Alpha Sound, we choose between using the NEXO processing or our own custom processing, depending on the application. Either way, we think it's always best to use NEXO subs for any configuration, because whether you're using their cardioid processing or using their omnidirectional processing with your own custom cardioid processing, you'll always want to be working with the best sounding subs that you can get your hands on. Now let's look at some volume plots. It's interesting that in the S118 back-to-back mode, we can see a slight EQ dip in the rear signal around this frequency. This dip may have been specifically added because the subs are so physically separated in this mode, the largest distance in fact I think they've ever come out with, that the highest frequency it can successfully make into cardioid without causing cancellations in the forward direction as well is lowered so much that it begins to extend into the usable range. Even with the crossover in this mode set to no higher than 60 Hz, a decision was probably made to slightly dip that frequency in the rear to avoid any potential forward cancellation in that upper range. Indeed, the S118 back-to-back setting does seem to perform the best at very low frequencies, better than the side-to-side mode, which is physically closer together and therefore must not have required a similar EQ dip as can be seen here. Even with the CD18, it seems that the front-to-back distance was great enough to merit an EQ dip in the rear, but the dip is a bit higher in frequency, probably because the CD18's depth is not quite as much as two S118s in back-to-back mode. It's interesting also that even though the crossover can go up to 120 Hz, the rear signal appears to be left crossed over at around 85, and those higher frequencies in the front simply don't experience any cardioid effect. This is seen even more drastically in the old CD18 140 Hz setting from before the introduction of the NX amp. Again, this must be because there is a physical limitation to how high of a frequency a set physical distance between boxes can successfully make into cardioid. As I suggested in my previous video, a possible future solution to this might be the addition of multiple drivers in the rear at different physical distances and with different delays, all handling smaller frequency ranges, from 30 Hz all the way up to 200 Hz or even higher. With the STM series, for example, the B112s could be crossed over in cardioid mode with the S118 subs at around 85 Hz. At Alpha Sound, we've experimented with using a number of NEXO boxes in this way. For example, at this vocal a cappella concert where we had cardioid CD18s flown in the venue and crossed them over with some B1 boxes that we configured in cardioid from 85 to 200 Hz, which then crossed over with the GOT rig around 200 Hz. The reason we chose not to rely on the GOT rig for the mid-bass cardioid, even though it has it, was because we needed a very specific cancellation angle to point right at the area condenser mics we had on stage for the vocal ensemble. Taking a closer look at the Joshua Bell concert from earlier, you can see that we used PS15s on top of the S118s to do a similar thing, running them in cardioid from 85 to 200 Hz, where they then crossed over with the GOS rig. It's a really powerful tool to have a cardioid response from 30 Hz all the way up to 200 Hz and higher, which can be aimed very specifically at sensitive microphones on stage. So now, let's take a look at why the maximum volume goes down when the delay is fixed at all frequencies. The basic problem is that by using this kind of cancellation method, some frequencies are made stronger because they sum perfectly together, while others are weakened because they don't. Here we see the isolated volume responses of both the front and back subwoofers, and also their combined forward response. In order to keep a balanced sound across all the frequencies in the subwoofer range, the stronger middle frequencies, which sum together perfectly, have to be brought down in volume, using a bit of EQ in the processor perhaps, in order to match the weaker ones on the edges so that the final response of the subwoofer setup remains flat. Even though the strong frequencies could get louder than the others around it if we really push the subwoofers to their limits, the sound will become unbalanced as the weaker frequencies fell behind in volume. The other option here is to boost the extremes where the weaker frequencies are instead of dipping the middle, but either way there's going to be a bit of unusable headroom at certain frequencies that again could get louder, but can't without ruining the overall balance of the sound. The subwoofer is therefore only as loud as its weakest frequency in its usable range, and just can't get as loud as it could if we had different delay times at every frequency in the rear like the NEXO processing, or if the subs weren't in cardioid mode at all and were summing together perfectly at all frequencies in omnidirectional mode. Now this brings up another issue. Let's take a minute and explore why cardioid subwoofers, in any configuration, are not ever going to be as loud as omnidirectional subwoofers. When two omnidirectional subwoofers are placed next to each other, and they play the same sound at the same volume at the same time, their waveforms sum together with a combined additive force of 6 decibels. A decibel is a way of measuring sound volume, and for reference, it is generally considered that an increase of 10 decibels is perceived as being twice as loud, and a 10 decibel decrease half as loud. When we make subs into cardioid, the rule of thumb is that their combined output will only be about 3 decibels. Of course, there's a lot more to the story. Here's a look in the forward direction at the combined waveforms from two omnidirectional subs, each producing a single cycle of 50 Hz. Their combined energy will actually result in a waveform that is 6 decibels louder. Now, let's look at the same set of waveforms produced by a cardioid setup. You can see that because of the delay added to the rear, the first section of the waveform from the front subwoofer stands alone. It is only the second half which is met by the inverted waveform from the rear. But then, the last half of the waveform from the rear again stands alone. For the one half of the waveform from each subwoofer which perfectly stacks up on top of each other, there is a 6 decibel increase. So the total waveform from a single cycle of a single frequency from a cardioid subwoofer looks like this. A bit different than the normal omnidirectional response. If we let the sound play out a bit more by extending the time over which the frequency is produced, we can see that the cardioid subs will always leave the first and last little bits of the waveform standing on their own. So what does this mean? Well, for transient sounds like kick drum and percussion, where there is probably only a few frequency cycles created each time there's a sound, cardioid subs are going to sound a bit quieter, because there's a lesser proportion of the total waveform in the forward direction that experiences the full 6 dB increase from the two subs, as opposed to its omnidirectional alternative where 100% of the waveform experiences it. Here's a kick drum waveform from the front sub with the corresponding waveform from the rear sub, and so this is the sum total cardioid waveform in the forward direction. Now here's what it would sum to if they were in omnidirectional mode. For prolonged sounds, such as bass guitar holding out a single note, the difference will be less dramatic because a higher proportion of the total amount of cycles do stack up to the full 6 dB, as seen here. Some people have said that because of this anomaly, cardioid subs don't sound as tight or as accurate, especially for transients. Personally, I don't really notice a difference. There's a lot of other factors which contribute to the relative tightness or accuracy of, say, a kick drum, such as the drum itself, the player, the microphone, the room, the overall quality of the amplifiers and subwoofers. I mean, I'll take a NEXO cardioid subwoofer over anyone else's omnidirectional product any day. But this does lead to another important point, which makes other cardioid configurations, such as end-fire, relatively ineffective in my opinion. In an end-fire setup, instead of delaying the rear subwoofer, the front subwoofer is delayed and the rear sub is not flipped out of polarity. And often several subwoofers are placed in line, each being delayed in proportion to its distance from the rearmost subwoofer in the setup. So as it looks in the software, there is near perfect summing at all frequencies in the forward direction, and a cardioid cancellation effect in the rear, with different frequencies having different cancellation patterns that shoot off in various directions depending on their wavelength and the physical distances between the subs. But higher frequencies will begin to cancel in both directions, and lower frequencies will often not cancel much at all. Now, this method is another attempt to maintain maximum forward volume while providing an average amount of cancellation in the rear, but without any consistency or precise control over the cancellation angles. Personally, I think that the amount of cancellation is very unimpressive because of its strange and extreme lobing effects, and it's often really impractical to set up because of the depth required for multiple rows of subs. But there is also a major conceptual flaw here which renders end-fire setups very ineffective in reality at even providing average cancellation in the rear, despite what the software says. In most prediction software, polar patterns are generated by using mathematical algorithms that assume a constant sound at a given frequency, not a quick transient, and the prediction is taken from the middle of the prolonged sound, like a kind of static or infinite calculation, a bread slice. But let's look at what happens in reality with two subs in an end-fire setup. First, we'll consider the forward direction only. We can see that the waveforms sum together perfectly. However, in the rear direction, since the rear sub is the first to fire, there will be a little bit of waveform which escapes out into the world that doesn't get canceled. The cancellation effect begins after this, but then at the end, there is another bit of waveform from the front sub that also gets through without any cancellation. This means that for most real sounds, and especially transient sounds, a very little proportion of the waveform will be truly canceled. Most of it will escape into space unaffected, and there may even be bits that sum together instead of canceling. The only kinds of sounds which will truly cancel are prolonged pure sine waves, and again, only the middle portions, the beginning and ending bits, will escape unaffected. This problem only gets worse when you start to add multiple subs, which most end-fire setups do. So these and other reasons are why end-fire cardioid subwoofer systems do not perform very well in my opinion. The prediction software used to model their cardioid polar pattern is usually only considering a bread slice in an infinite sine wave, which makes its cancellation effect very weak for most real sounds, especially transients, and there is no way to direct the precise cancellation point at all frequencies if needed, and they can take up a lot of physical space because several rows of subs are often implemented to try, in my opinion unsuccessfully, to broaden the range of frequencies which get canceled. Anyway, as always, I'd love to hear your creative subwoofer ideas. In a future video, I'll talk about some really practical tips for setting up your own custom cardioid subwoofer configurations. Check out alphasound.org for more fun information and technology, or follow us on Facebook. Thanks for listening.